Yeah. I'm really sorry. I was looking at the wrong clock, which was not moving. So good afternoon, everybody. Just to make sure that you can hear me everywhere, and then in Zoom that you can hear me. So welcome to the 64 faculty lectureship at NDSU. My name is Estelle Leclerc. I'm a member of the Faculty Awards and Recognition Committee. And on behalf of this committee, I would like to welcome relatives and friends of Dr. Mila Kryjevskaia, and all the members of the community, the NDSU community, Provost Bertolini, faculty, staff, students, and all those joining us online. So this year, the award committee has recognized Dr. Mila Kryjevskaia as the recipient of the lectureship, one of the most prestigious awards at NDSU. But this afternoon, we would also like to recognize Dr. Jessica Stryker, Professor of Mathematics at NDSU, and Dr. Chanchai Tangpong, Professor of Management at NDSU, who were nominated for this honor and were selected as finalists by the award committee. So I would like Dr. Stryker and Dr. Tangpong to stand so we can recognize them this afternoon. So thank you. Now a few words about the faculty lectureship. The faculty lectureship recognizes sustained professional excellence in the three areas of teaching, scholarship and creative activity, and service. Dr. Kryjevskaia has achieved impressive accomplishment in each of these areas, and you will hear more about them in a few moments. Dr. Kryjevskaia is the most recent of more than 52 recipients of NDSU faculty lectureship dating back to 1957. Examples of topics that have been presented during this lectureship include Arctic exploration, a biological frontier, the conductor art of ice and men, quoting from the caveman to Apollo 8, a new world order, and 2 years on the pandemic frontiers. These are just a few examples of the topics that have been presented. So just a brief announcement. There will be time for some questions after the talk of Dr. Kryjevskaia. And those who are joining us remotely today, they will be also able to ask questions at the end of the lecture. So now it's my pleasure to let Dr. Kimberly Wallin, the Dean of the College of Art and Science, to introduce further Dr. Kryjevskaia. Thank you.
Thank you. All right, good afternoon, everyone. It's my pleasure to introduce today's speaker, a distinguished educator, researcher, and a national leader in physics education, Dr. Mila Kryjevskaia. Yeah, okay, great. Mila is a professor of physics in the Department of Physics and also in the STEM education PhD program here at NDSU. Her research stands at the intersection of physics and cognitive psychology, where she focuses on uncovering how we learn and think, not just to deepen understanding, but to drive innovative teaching. She plays a vital role in advancing research-based teaching methods at the national level, and she currently serves as the vice chair of the American Physical Society Committee on Education. Today, she invites us to examine a force that shapes all of our thinking, intuition. While experts often rely on intuition as a powerful tool for problem solving, novices can find it misleading or even frustrating. Drawing from insights on physics education, research, and cognitive psychology, her talk will explore how intuition can both empower or derail our reasoning, and plus how we can learn to harness it wisely in physics and in life. So please welcome me in joining Mila to the podium.
All right. Well, thank you very much for coming to my talk. I'm extremely humbled. Give me a moment. I'm extremely humbled to be among outstanding educators who received this award before me, and to among those who were nominated for this award this year. When I received the email notification, I triple checked it to make sure that it was addressed actually to me and not to somebody else. And when we faculty give award speeches, we like to say that, we're not here for the awards, we're here for the students and for the work that we do. And I definitely share this sentiment. But I also want to say that I'm here for a bit of a selfish reason too, because I love my job and I don't want to do anything else. And sometimes I ask myself, how did I get so lucky? And then I realized that luck has a lot to do with it, but also it's the community of people who supported me along the way, starting from my loving, caring, nurturing, well-educated parents, and ending with my current collaborators and faculty in my department and at NDSU. So I would like to say thank you to everybody who supported me along the way. Thank you to faculty and students in the discipline-based education research program. Thank you to the deans and the provost office for supporting my department and me in it. And also, of course, I would like to thank the committee members. I hope my presentation will not disappoint. And of course, the greatest, the huge, I don't have words to describe my gratitude to my physics colleagues for always having my back. And, all these gestures of support, big and small, they just do not go unnoticed. Let me give you a couple of examples. I remember during my second and third week at NDSU, I was teaching and coming back from giving a lecture, and I guess I was disturbed because towards me, Orf Svensson was walking, and he looked at me and he said, "So, how is teaching going?" And I said, "Not well. I just made a mistake in class." And he just smirked and said, "Only one?" Orf, do you remember this? Orf doesn't remember this. But just these two simple words just completely changed my mood. And another example, maybe a couple of months later, the then chair of my department at the time, Daniel Kroll, he is retired by now, stopped by my office to check on me. And so he said how it was going, and I told him everything I thought about how it was going at the time, that 95% of my time was dedicated to preparing to teach. The rest was dedicated to me attending various meetings. My research is not going anywhere. I'm deeply concerned. I'm failing. And so again, Dan just looked at me, smiled, and said, "Don't worry about that. You will adjust. Just remember to capitalize on your strengths." And I have been doing that ever since. So thank you to my physics colleagues for continuing to nominate me for all sorts of awards. And after so many failures and rejections, I actually would have quit, but you didn't. And if it's not a lesson in resilience, then I don't know what is. I also would like to thank my family. My daughter is here. Hi, Maria. Thank you for coming. And finally, I also would like to thank my students for being kind and hardworking and brave. So I realized that when you learn something for the first time, it takes a lot of courage to ask questions, to argue with me, to make mistakes publicly. And thank you for tolerating mine. I very much appreciate it. And let's be honest, physics has a reputation. It's the kind of subject that people love to fear. And so the question is, why is it happening? And this is one of the things that I would like to talk to you about today. I'm not going to tell you that physics is easy. It is not easy. It is hard. Sometimes it's painfully hard. But what isn't? Every single learning experience which is worth taking is actually also worth failing. I'm also not going to tell you that people who learn physics don't make mistakes. They make mistakes all the time. But who doesn't? Okay, so to make my point across, I actually have 3 questions for you. Are you ready for my questions? All right, so if you thought that you will be just sitting here listening to my talk, you made your first mistake. All right, so here's what I want you to do. I'm going to ask you questions. And as soon as you feel comfortable enough to give me the answer, give it to me. Just shout it out. Play this game with me. The questions are not about physics. And frankly, I don't even care if you answer them correctly or not, okay? I just want to know how you think. Are you ready to play? All right. So here's my question. I'm asking you to finish the sentence. Bread and butter. Nice. Accepted. 2 plus 2 is 4. Accepted. A jacket and a shirt cost $60 in total. The jacket costs $50 more than the shirt. How much does the shirt cost? Everybody thinks $5? 10? So all right. So, if you are like me, when I saw a question like that for the first time, my first response was $10. And many students actually give this time of response, not only students, everybody, many people give this time of response without actually stopping to think and checking whether or not it's right. But it is, in fact, not right. And you can recognize this mistake very briefly without necessarily learning any additional math skills, right? Because if the shirt costs $10, then the jacket would cost $60. But then together they would cost $70. So $10 is obviously an incorrect response. And most learners very quickly recover and tell, yeah, I made a mistake. The correct answer is $5. So the question is, do you make this kind of mistakes? I do. Do you think our students make this kind of mistakes? I do. But what does this type of error mean? Is it the lack of knowledge? Doesn't seem so, because we all figured out the correct answer to this question without necessarily gaining any new mathematical skills. Is it poor understanding? Is it weak reasoning? Maybe it's a lousy teaching on my part, entirely possible. Maybe it's all of the above, or maybe it's something else. So let me give you an example of this type of reasoning from my physics course. I see some of my students here. So this talk is for you, okay? I want you to argue with me, I want you to challenge me, and I want you to disagree with me. All right, so here's one example from physics, Newton's third law. If you walk into any physics classroom, especially in a college classroom, and if you ask, do you know what Newton's third law is all about? There is always going to be somebody who would say, yes, it's the action reaction, right? I mean, I may be confused between is it Newton's first or second, but I know that the third one, it's the action reaction. If you push your students a little bit further, they will tell you a little bit more. They would say, oh, yeah, it's the one that says for every action, there is an equal and opposite reaction. Is that right? Yes, that's right. And so we
see. Now I'm going to get into a ball behind Joe, and I'm going to apply a force to him.
If I exert a force on you, you will exert a force on me, which is equal in magnitude and opposite in direction. And it's very easy actually to believe that that's how physics works, because after all, when we walk, we exert a force on the ground exerts a force of us, that what propels us. When we fly, we exert a force on the air, and the air exerts force on us. When we jump, the same thing happens. And so believing in Newton's third law is not particularly challenging for most of the students. And in fact, they can successfully solve quite complicated physics problems. For example, right here, you have two blocks. These two blocks are on the platform, the whole platform accelerating upwards. And if you ask them to compare the force that object A exerts on object B and object B exerts on object A, they're going to tell you that they are the same. Because according to Newton's third law, that's the reply. And you know what? What do? We celebrate, because this response, this success rate is actually quite rare in physics, 85% correct. And to me, as an instructor, it tells me that my students not only learned what Newton's third law is all about, they can recognize its applicability in a situation which is actually quite untrivial. So we celebrate until we see the next task. There is a light car and a heavy car, and the heavy car moves towards the light one, and they collide. And during the collision, would the force that object A exerts on object B be equal in magnitude or greater or less than the force that object B exerts on object A? It doesn't matter whether you ask this question before instruction, during, or after. There is going to be a lot of people who would immediately say a heavily moving car exerts a greater force. And when they learn that it is incorrect, they're actually quite surprised. They say, how could it be? But it makes total sense. And if you ask them a little bit more, what kind of sense? They say common sense. Because if you think about a light car colliding with a heavy truck, after the collision, the light car could be completely destroyed, while the heavy truck can leave just the scene completely unharmed. But the problem is that I'm not asking you about the damage that the objects sustain. I'm asking about the force that these two objects exert on each other. And I believe this is something that in cognitive psychology people call attribute substitution. I'm asking you about the force, but you're answering my question based on the degree of damage. All right, well, you know, quite often there are students who just are not satisfied with my answer. And sometimes they come to me and say, all right, so Dr. K, are you saying that if somebody punches me in the face, then the force that the fist exerts on my face is equal in magnitude and opposite direction to the other one? And that is exactly what I'm saying. Again, for the same reason, because I'm not asking you about the level of pain you can endure or the damage to your face. I'm asking you about the force. All right. You may say, well, but this is just most difficult, counterintuitive kind of law, and you chose it to demonstrate something to us. But we see this kind of inconsistencies in student reasoning throughout introductory physics courses and beyond. And I bet you can also think about a couple of examples similar to that when students in your discipline, in your classrooms, think like that. But it doesn't mean, you know, that there is something wrong. First thing, that if you are students, I want you to know that it is indisputable that knowledge is central to productive reasoning, but it's not enough because oftentimes there is intuitive thinking which just feels so right, which opposes the formal reasoning that just feels so wrong. And there is a frequent conflict between the two. And oftentimes we need to be able to resolve this conflict, and that requires some skills. So it doesn't mean that we're bad reasoners. In fact, this kind of reasoning patterns are completely normal, and they could be explained through the lens of dual process theory that was recently popularized by Danny and Kahneman. If you read this book, Thinking Fast and Slow. And so what does it say? It says that there are two processes engaged in most reasoning tasks, process 1 and process 2. And I will let you experience each one of them. Here is process 1. Ready? Process 1. The moment you saw the picture, you immediately recognized that the woman is angry. if she was in this room, you probably want to get away as far away from her as possible because you will sense danger. This is process one. It is automatic, subconscious, quick. It just suggests a way of thinking about a certain situation without any effort. And here's process two, 17 times 24. Do you have an answer to this question? Does anybody have an answer to this question? Well, you can give me any number. I wouldn't know whether or not you're right. Because I used this slide dozens of times. I never bothered to stop and calculate. Why? Because it's not necessary to get my point across. Because if we could avoid engaging in process two thinking, we would. And it is the case here that process two is deliberate, effortful, it is orderly, and quite often it is also painful. And as I said, if we could avoid it, we probably would. So when I became familiar with the dual process theory for the first time, I thought, I get it. This is me, I'm process two. I understand that there are some people who are kind of, shallow, who speak before they think. I am not one of them. When I see a problem, I actually start thinking from fundamental principles. I build my argument carefully and logically. That's who I am. And you know what? I want my students to be like that. And guess what? I was absolutely wrong, as I often am. It turns out that process one cannot be turned off, whether we want it or not. Process one immediately and subconsciously produces a way of thinking about the situation. And that is what we call intuition or gut feeling. So I like this definition of intuition by Simon, who says that it's nothing more and nothing less than recognition. I think the biggest confusion that I see when I talk about intuition with people is that oftentimes they define intuition as something based on everyday experiences. I would argue that it's not the case. Intuition of novices might as well be based on everyday experiences, but intuition of experts actually has a lot of formal knowledge that becomes automated. And so when an expert sees any new situation, this automated knowledge becomes intuitive. And therefore, a definition of intuition as the first available response holds for both experts or novices. Okay, let me go back to the beginning of my talk. Do you remember that question, 2 + 2 is 4? So do you think it's the kind of answer given by process one or process two? All right, raise your hand if you think it's process one response, 2 + 2 is 4. And raise your hand if you think it's process two response. A couple of people. Okay, I actually agree with Crystal, who said it depends on the age. For us, 2 + 2 is automatic. It is completely and totally intuitive. But think about your children who are learning how to count. When they come to you and say, Mom, look, I just learned 2 + 2 is 4. And they show the fingers and they count 1, 2, 3, 4. This is process one and process two working together. She probably recognizes that to find the answer to this question, she needs to use her fingers. This is process one response. But to find the answer, she actually needs to engage in process two and do the mental calculation. So that's why intuition of experts is very different from the intuition of novices, because experts have a large repertoire of relevant experience. And so now they recognize any given new situation accurately quite often. But the novices do not have this repertoire of experiences yet, and therefore, most often they make mistakes. But if the result of process one, if the intuitive answer is so appealing to us, then oftentimes we just go straight to the final response. But it's the job of process 2 to intervene when necessary. All right, so again, since process 1 cannot be turned off, I think it's important to realize that we are going to make mistakes. And so error detection and override is absolutely normal. And again, I'm looking at my students. It's absolutely normal. It should be expected. And it's not an indication of any source of deficiency or failure. So my collaborator and I actually used the dual process theory to develop a model of how we think about our students' reasoning. And I really like this model because it allows us to visualize reasoning pathways, but also identify reasoning hazards that we reasoners, including our students, are likely to encounter along the way. And so I would like to share this model with you. Maybe you will find it useful too. We all come with prior knowledge, experiences, and expectations. That's indisputable. The moment the task is initiated, our quick and intuitive process 1 immediately recognizes this task in a specific way through the lens of our prior experiences, knowledge, and expectations. The problem is, as I already told you, that this recognition for novices is quite often inaccurate. And that faulty recognition often presents the very first hazard on the reasoning path. So if you are a novice, you might get on the incorrect reasoning path from the start. But that's okay, right? Because we also know that it's the job of process 2 to intervene and correct the mistakes. As I already told you, oftentimes when we feel confident in our intuitive response, we may completely circumvent this process 1 and immediately come to the conclusion. I believe in cognitive psychology, this path is called path of cognitive miserliness. This kind of name reflects the human's tendency to spend least amount of time possible on any cognitive task. So my collaborators and I actually decided to soften the blow a little bit and call it a path of cognitive frugality. I think this name reflects a little bit better that for experts, it's absolutely unnecessary to engage process 2 in checking all possible answers. If we stopped every time we needed to calculate 2 plus 2 is 4 to check whether or not we're right by counting our fingers, we wouldn't get too far. So that's why we like this name, path of cognitive frugality. And so for novices, however, if this path of cognitive frugality is a mistake, that presents the second hazard on the reasoning path. Okay, but that's okay. Imagine that we avoided this hazard and process 2 is engaged. Unfortunately, process 2 is ridden with biases of its own. We do not just spontaneously look for alternatives. And even if we do, we tend to look for evidence that supports what we already believe to be true, confirmation bias. And so reasoning biases present the very third hazard on the reasoning path. In physics, for example, one example of such biases would be when people oftentimes use correct equation to interpret them in a specific way that would justify what they believe intuitively to be the answer. I see it all the time. All right, but let's say that we feel uncertain about our answer. If our relevant knowledge is weak or missing, we wouldn't be able to consider alternatives and decide between the better option. And that is the fourth reasoning hazard. And therefore, even if the process 2 is engaged, oftentimes the intuitive response still produces the final conclusion. But of course, we change our mind. We can go over this process a couple of times. We may correct our biases and get to the right answer. That's fine. Okay, but you may ask me, this is all very good. But again, you're talking about physics. Physics is very abstract. It deals with math. We just do not have any intuition about abstract ideas or about math. All right, that's fair. So let me give you an example. So let's consider electric field. What is it? Well, we know, I think you're not going to argue with me. I hope you agree that if we have two charges, they're going to interact with each other. We know that the big one will produce a force on the little one, and the little one would produce a force on the big one. And look how beautiful physics is. Newton's third law works here too. Even though this question is not about Newton's third law, but I just want to tell you that it works here too. And so here's the mathematical expression that tells us how to calculate direction and magnitude of the force on the little one or on the big one. And you can see that right here you have the product of both charges. So this is totally consistent with the Newton's third law. Okay, so this is one way of thinking about charge interactions. A different way is to say, you know, let's just think about it this way. A charge changes the space around it. So this changed space we're going to call electric field. And when we place another charge in this electric field, then this electric field itself is going to exert a force on the yellow charge. Does it sound good? It sounds reasonable. All right, so we just discovered the concept of an electric field as something that a charge produces by changing the space around it. Now, we have this concept. We need to define it. In physics, we define concepts by developing a way of measuring it, right? So I ask my students, how are we going to measure it? And it's not an easy question. And after some consideration, somebody usually would say, well, we know how electric field interacts with charges. So if we put a charge right here at this point, and if we measure how much electric field affects it, in other words, how much force is going to exert on it, then we would know whether electric field is strong or not. Agree? Agree. All right, so it's very reasonable to say that the stronger the force that the yellow charge feels, the stronger the electric field. But then what happens if instead of 1Q, I actually have a different charge? What if the charge that I use to measure my electric field is now twice as strong? What would happen to the force that it feels? And again, my students usually tell me absolutely correctly that it's going to feel a greater force. This is right. The charge is going to feel the greater force. But what about the electric field produced by the green charge? Is it any different? No, it's not. So how could it be if we think that the electric field is proportional to the force that our measuring instrument, the test charge, feels? Then we are running into trouble. Well, don't worry, my students usually produce a solution. They say, all we need to do, and it's not an easy, by the way, it's not an easy thought, but somebody usually says, we just need to measure force per unit charge. And that is absolutely true. If we take the total force that the charge feels and divide it by the total charge, okay, so it's supposed to be Q test, and divided by the total charge that experiences that force, then we get an electric field. And now it's independent of what kind of instrument we're using to measure it, whether it's 2Q, 5Q, 6Q, 10Q, the force is going to change proportionally. I tell my students, when we think about it this way, it feels very easy, which is a good thing, I suppose. So now we can use this definition to actually determine what the electric field due to a point charge is. Like now we know what the force is, so we can just put it back in the equation. And so we can calculate something that makes total sense, since the force depends on our measuring instrument, on Q test, and then we divide it by the Q test, the value of the measuring instrument that we use to measure that electric field completely disappears from the picture. And what we see that the electric field produced by this charge only depends on the value of this charge and the distance to the point that we're measuring. Okay, nice. And then about a week later, I asked my students to consider quite relatable situation. We just landed on a distant planet, and we need to measure electric field on the surface of that planet. So what do? We take our handy measuring instrument, charge 2 coulombs. We are going to measure the force that this charge feels. I give them the value and ask them, so what's the electric field that we're measuring? So it's a trivial problem. Everybody answers it correctly. You just take the force and divide it by the charge, not a problem at all. But the next question is, all right, suppose that instead of 2 coulombs, you use a different charge, 6 coulombs. What would be the electric field that the new 6 coulomb charge would measure? Okay, so what is happening here? A lot of people say, well, you just increased the test charge, so the electric field must decrease. This is something that I'm convinced is a completely intuitive type of error. It is completely an erroneous pattern recognition error. Because when we learn math, this is what we see. We see y is equal a over x. In math, x is typically a variable and a is a constant. So if somebody tells me what would happen to y if x is increased, with high degree of certainty, I'm going to say y is going to decrease. You know why? Because friendly mathematicians use symbols a, b, and c to represent constants. And if they don't, they usually tell us what those symbols mean. I don't know what this is, but this is evil. Because if you tell me what is going to happen to b if c increases, there is an infinite number of correct solutions. It's possible that a is a constant, but maybe a is going to change proportional to c. Maybe a is going to increase by a greater factor so that both b and c are going to change. And here's physics. So if you tell me that the test charge increases, I'm not keeping secrets from you. You know what F is, but you need to determine it on your own. You need to recognize, is F a variable? Is it a constant? Is it a function? What is it? And in this specific case, it turns out to be the kind of quantity that linearly depends on the test charge. So the electric field is not going to change. So this is in my mind, this is a typical example of incorrect pattern recognition. The problem is that these kind of equations appear in physics. This is a single course, 1 semester course. They appear over and over again. And an interesting thing is that to answer this question correctly, the students didn't need to use the math. They could have just told me what they told me before, that if you do not change the source of the field, like we didn't do, the electric field is not going to change. But they don't like reasoning this way because they don't trust their conceptual understanding in physics. Mathematics never fails. So the very first time I taught this course, I had a student who actually challenged me. The student said, he totally did not believe me. The student said, so what are you saying? That math lies? Well, it's either math or me, right? Which side are you on? Definitely not mine. Math does not lie. It just has a hidden agenda. And you need to learn how to deal with this hidden agenda. All right, so what are we going to do about it? Well, I would like to use, how much time do I have? Okay, I would like to use this analogy to actually outline a little bit instructional implications. So imagine that you are starting your journey over here. And imagine that it's not actually you because you're experts. Imagine that it's your student. You tell your students that the final destination is going to be the lowest point in the terrain. They don't know it yet, but the actual final destination is right here behind the hill. So to get there, they have to expend some efforts. But the process one points them towards an easy path to a local minimum. Once there, they may not recognize that they reached the incorrect destination. Maybe they were there before. Maybe it just feels beautiful. But even if they are in doubt, they may not have the skills and equipment to get themselves out of the hole. Experts, on the other hand, possess relevant experience and very sophisticated hiking gear. They can get out of the hole with ease and actually get to the target destination. Another possibility, another scenario for experts is that it's possible that they traveled this path so frequently that the whole terrain changed for them. This path now became so worn out that it doesn't represent any effort at all. So this analogy kind of suggests a couple of instructional approaches. First, we can actually help students change the terrain and wear down the path so that intuitive idea becomes completely consistent with the formal response. But this approach has some drawbacks because you cannot train on all possible hiking paths, and a little bit change in the initial or final destination is likely to get our travelers lost. However, we do advocate for this approach to be applied when we're thinking about essential skills. Like in physics, for example, it would be vector addition, subtraction, setting up basic integrals, differentiation, and so on. If we automate these kind of skills, that more cognitive resources could be released and used for more cognitively demanding tasks. And here's another approach, is to give students opportunities to make mistakes, recognize when they get into the hole, how to get themselves out of it. And after all, physics is not that much different from the hiking. So you train, you go, you fall, you get up, you cry, you turn around, you come back, you train more, you attempt again, you fall again, maybe you'll get a little bit farther, and at some point you'll get to the top. And it doesn't have to be Mount Everest for you to enjoy the view. So thank you very much. And I want to invite everybody to join us to study physics. This is our physics department as envisioned by my department chair. We're a lot of fun. So we have cats and dogs. We have bats right here. We have a guitar. We have everything. And of course, I would like to acknowledge National Science Foundation and Discipline-Based Education Research Group and my collaborators, and of course, my students. I'm looking forward to my students challenging me on this talk. Thank you.
Thank you very much for this very excellent talk. So we have time for questions. If I can take this out. Yeah, it's on. So we have time for a few questions from the audience.
So one question that kind of came to my mind from learning physics, is there also kind of some value, or like have you investigated like ignoring intuition because like that it's kind of wrong? Because like in learning quantum mechanics or like higher level physics stuff, it feels very weird as you kind of, or at least I have kind of learned to like ignore it whenever initially approaching a problem, just trust in the math and then develop the intuition later on. like, I guess kind of my question is like, have you like heard of that before? Like, has that come up prevalently in your research?
Well, I agree with you and disagree with you at the same time. I don't advocate for ignoring your intuition. I advocate for acknowledging your intuition and recognizing that you need to modify it. So trusting in math when you learn quantum mechanics, getting better at pattern recognition in this new and completely weird subject is perhaps a way to go. But it doesn't mean that you need to ignore your intuition. You need to acknowledge it and refine it.
Thank you.
I could probably ask my question without.
It was the audience online, people online.
Oh, yes. Following up on the question, is it possible to actually ignore intuition?
Well, you know, according to the dual process theory, you cannot turn it off. So whether you want it or not, it's going to inform your reasoning. So when you say ignore intuition, you can't ignore. You immediately have a sense of what the problem is all about. Even if your sense is that I'm always wrong on this type of questions, this is still your intuition. That's why I advocate for acknowledging this intuition. It doesn't mean that you have to act on it, but you have to recognize. I also want to say that, you know, when people talk about intuition as pattern recognition, oftentimes they talk about recognizing applicability of specific knowledge to a specific situation. But I would also advocate for recognizing scenarios where you know you're more likely to be wrong. This is also the kind of intuition that needs to be trained in my mind.
Repeat it.
Uh-huh. Yeah.
So the question from Zoom is, what is the evolutionary purpose for the development of intuitive thinking?
Oh, yes. What is the evolutionary purpose for developing the intuitive thinking? It's a very good question. So if you remember when I introduced the dual process theory the very first time, I let you experience process one. And so I told you that you immediately recognize the danger. That's the evolutionary purpose of process one. Survival. We need it to survive. That's why we cannot turn it off. We just need to acknowledge it and learn to love it.
I was wondering if you could comment on the role of laboratory work in helping students avoid some of these pitfalls in reasoning, because it sort of struck me in your example of the collisions, there's this outcome you can very easily imagine, like you said, about sort of the damage on the lighter vehicle. But then in the lab, if you actually measured forces, you would have this experience of seeing that there was a difference between something you measured in the laboratory and this sort of outcome you could see. And I wonder if there's any evidence suggesting that helps students sort of anchor themselves in a measurement and something more formal that they did in a hands-on experience like that.
Yes, yes. So there is a well-known approach in physics education research, which is called elicit, confront, resolve. So this approach is based on, I believe, what you're referring to. So first you ask your students to predict an outcome, and by predicting, most often that will elicit most intuitively appealing responses. Then confront, do an experiment to show, to collect the evidence for, collect data that would allow you to either validate your prediction or reject it, and then resolve. If you see that your data does not support what you predicted before, then you do it from the process of conflict resolution. Yes, it's a very good approach. Unfortunately, in physics, many labs oftentimes are designed in a way that confirm as opposed to discover. So that's why, as anything else, you know, you need to tailor your instruction for your instructional purposes. So yeah, thank you. Thank you for your question. I believe it should work. Yep.
I think there was another.
I wonder if you have any tips for mortal educators on how to persuade students to be more reflective and engage in this approach to learning, to confront their intuition and you know, activate system 2.
You know, again, it's a very good question. I do research related to how people think, but I'm not going to claim that I'm actually a good implementer of what I preach for. I think when I think about my own teaching, the biggest thing that I think my teaching lacks is that my students do not see my struggle, because I prepare well when I come to class. I review my lectures. I know what problems I'm going to solve. I know how I'm going to solve them. So they don't see my struggle when I come to class. And when I make a mistake, I told my students right away that I guarantee to you that I'm going to make a mistake. But when I do, I still feel kind of, you know, uncomfortable. So I guess the best way to persuade your students that making and correcting mistakes is a good thing is actually to reveal that you are making mistakes yourself. Maybe the mistakes that I make are not noticeable for my students because I do not make the same type of mistakes that they do. I already passed that stage. I struggled enough. And don't you guys agree with me that sometimes when most people in my class make a mistake, I actually tell you that I made that same exactly mistake when I learned it for the first time, because I already passed that stage. I'm not making these mistakes, not because I'm smart or whatever, brilliant, but because I already struggled enough. I make mistakes every day, but in a different circumstance. I do it in my research. This is something that keeps me humble. Right? And so when I talk to my students, first of all, I do not hesitate to tell them that making mistakes is normal. I make them all the time. And I'm going to make mistakes in this class, even though I taught it many times. And I do make mistakes. And they forgive me, right? All right. And another thing, I actually invite my students to argue with each other. I don't know how successful I am, but I was actually trying really hard. And sometimes they do. And that's the best moments of my teaching. When I see two people across the room arguing with each other, I just can turn around and leave. They're fine. They're doing fine. I taught them what I wanted. So, and that's why I want to thank my students for being so brave, because the only way to persuade somebody is to normalize making mistakes. This is totally normal. We can't avoid it. That's what the science tells us about.
The question from Zoom, is intuition universal, or is it affected by either cultural influence or early education styles?
Well, it's a good question. I would say that if we follow the definition of intuition as pattern recognition, I guess it gotta be affected by cultural differences. It's you develop intuition based on your prior experiences. When you live in a specific culture, your intuition may be different from intuition of mine. I was trying to, I don't think I would be able to give you specific examples, but just follow the definition of intuition as pattern recognition, and I think the cultural differences, the upbringing, it all influences the way you think.
There was also a follow-up to the question about the evolutionary purpose. What is the role of intuitive thinking in non-survival scenarios? And is it just an unnecessary burden, or does it also serve some function for us outside of the avoiding the poisonous berries or the saber-toothed tiger scenario?
So if we're not in a survival situation, okay, I accept the challenge. So, you know, when I was talking to you about automating certain skills, like multiplication table, some of the answers to, you know, 6 times 6 is 36. This is your intuition. It helps you to reason productively, even if you are engaged in physics problem solving. If you didn't have this intuition, well, you can call it memorization, that's fine. But I also call it intuition because it's the kind of knowledge that automated. And so these automatization serves its purpose. It just releases some cognitive resources that we would be spending otherwise on repeating the 6 + 6 + 6 10 times to get to the answer 36. It's just more cognitive resources could be rerouted to more computationally demanding problems. That's my answer. Wow, who asked this question? Very good question. Okay.
Okay, thank you. Thank you very much again. Let's
Yeah,
give another round of applause.
Thank you all for coming.
And with this, I will give now
Yeah.
to Robert to
Yeah, I'll
Robert
get the
Superto.
close. Yeah, thanks. Thank you, Mila, for a great lecture. That was excellent. I'm probably the luckiest person here because I get to point out why this is really important and to thank Mila for a great lecture. You know, the faculty lectureship represents the great why NDSU is great, right? I mean, it allows us to pick someone who's brilliant and creates new knowledge for us, but also has the ability to share it with us, right? So its ability to create knowledge and to teach. And that's why we're great. And that's why we have such high expectations for this and the long lineage of it. So in that sense, I'm just grateful for this. It was absolutely brilliant. And if I can put a sharper point on this, is that with the challenges facing higher ed, it's just great to be on a spectacular day like this, that we can come out swinging so strongly and to show why we're so good and why it's so important. So thank you for that. On a personal note, I can never resist this, but physics runs long in my recent family because I married into, my wife's father was a physicist at UPenn. And it's really ironic that this all ties together because, you know, early in our relationship, I found was, you get trapped in a room with a physicist for the first time while you're dating their daughter. And he's talking about it and he said something about his favorite class was Intro to Quantum Physics. And I was like, God, that must be hard. And then I asked the dumb question, like, how do you do that? And then an hour later, he was very passionate about it because he did care, he wanted to do well. And then miraculously, somehow, while we're in the living room, pulled out all these materials. Like, I don't even know where they came from. But it was spectacular. So you shared yours. So it's a really nice sort of coming around. And it kind of bumped up to my son. He's 14 years old. He says he wants to get a physics degree. Today, right now, his favorite physicist is Richard Feynman.
We're friendly people, yeah.
That's a long story, but he's changed favorite physicists, but we'll see where it goes. But anyway, the point of this is that thank you so much. You've done a wonderful job, and I'm honored to say that you rose to the challenge. It's not easy to be selected for this, but thank you so much. And to commemorate that, we have this framing of your poster.
Thank you.
And we've learned a lot. And for the folks in the room, we can go outside here and continue the conversations with Mila and everybody else because we have cake and things like that. For the folks at home, if you hurry, you can join us out here as well because you won't be shortchanged. But thank you everybody for coming, and thank you.
Thank you.